Imagine you are crossing a bridge, trusting it to support your weight without a second thought. But have you ever wondered about the invisible forces at play that keep that bridge standing strong? And one of these crucial forces is shear force. Shear force is a fundamental concept in engineering and physics describing how internal forces act within a structure when external loads are applied. Understanding shear force is essential for designing safe and efficient structures from bridges and buildings to aircrafts and machinery. In this video, I will solve two examples showing you how to draw shear force diagram. This is part of my video series on IStructE certificate in structural behavior, or if you're someone who is looking to improve your basics of structural engineering, this video is for you. So get your pen ready. Let's get started with our first example. By the way, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer in structural engineering and design at University of East London, and in here we'll learn about structural engineering. In this question again, we have to find out the correct shear force diagram. Ignoring self-weight and anti-clockwise shear forces are drawn positive. This is a sign convention which I will use here as well. Anti-clockwise forces are positive, and this is how we draw it on a diagram. Above baseline we have positive, below baseline we have negative forces. Let us see what options do we have. There are four options to choose from, and I will closely see where loading is applied. So in the middle of the beam I have this point load, so it means that between this point and end point there should be straight horizontal or vertical lines. There can't be any inclined line, so I will discard certain options because of that. Between this midpoint and the support here I have distributed load, so distributed load will have inclined lines and shear force. Firstly, there can't be inclined line over here. It means that this option is completely wrong. Secondly, this option is wrong as well because there are inclined lines. It looks more like a bending moment diagram instead of a shear force diagram. It means I can discard this option as well. It leaves me with two options. Option A is wrong as well because here we have loading applied, and between loading applied and start of UDL, which you see over here, we have UDL. Between point load and UDL, it has to be a straight line. It can't be inclined line. So here it is inclined line. It means it is incorrect. So the correct option must be option B. By process of elimination, you saw that I was able to find out the correct option. But if you didn't have that luxury of having options, then you can assume some values and carry out some very simple calculations to come up with the answer. That's what I'm going to do next. First, I'm going to take some assumption. Assuming that point load is higher than distributed load, the point load is applied here. UDL is say 10 kilonewton per meter, and here it's 4 meters, 2 meters, and 2 meters. Call this point as A and I call this point as B. There will be reactions over here. I call this as VA and I call this reaction as VB. Let me say summation of moment at A is equal to 0. First, let's take into account UDL. So 10 times 4 times 2. This will be reacting at half of the distance. Distance is 2 meters. And this is creating a clockwise moment with respect to A. That's why it's positive. And assuming this load to be, I did not assume this. I'm assuming that the point load is 60 kilonewton. So minus 60 times 6. The reason it's minus is that it is creating anti-clockwise moment with respect to point A. Minus VB times 8 is equal to 0. So 40 and 80. 80 minus 6 times 6 is 36. So 360 minus VB times 8 is equal to 0. This will be minus 20. So VB will be equal to minus 280 divided by 8. this will be minus 35 kilonewton. It means that direction is not upwards, it is downwards. I can say that here it is downwards 35 kilonewton. So VB is downwards. So if I sum up all the forces, summation of vertical forces is equal to 0. I have VA, I'm taking upward forces as positive, plus I have UDL, that is 10 times 10, plus I have 60, and minus 35, which is VB, is equal to 0. Minus 40 plus 60 is 20, plus 20 plus 20 minus 15. If I bring it on the other side of the equation, it will give me VA as 15 kilonewton. So once I've got loading, then I'm in a position to plot the diagram. Let's draw the diagram. First, it would be minus 15. It will bring it down here. Minus 35, not 15. And then it will go straight. So 35 and 60, it will give me plus 25. This is negative. So here I will have 25. And between 25 and this point, I haven't got any loading. So it will go straight. And between this point and end point, I have UDL of 10 kilonewton per meter, so I will subtract. This is plus. So 25 take away 40 will lead to 15. So here I will have minus 15, and then I have an upward reaction of 15. This is negative. In this way, I can plot this diagram, and looking at the diagram, B is the correct option. Let me now move to the next question. Here we have to identify the correct shear forces. Ignoring self-weight, anti-clockwise forces are drawn positive. This is a sign convention for anti-clockwise forces. These are drawn positive, and positive is drawn above baseline and negative is drawn below baseline. Let us see what options do we have. First and foremost thing that I would like to see over here is that I can break this beam into two parts. Here I have internal pin. I can treat internal pin as a hinge support or a pin support, which will mean that I will have some kind of forces over here. I will have upward force over here, and I will have downward force on the other side. So on right side I will have upward, on left side I will have a downward force, and that force will be equal to total load W times L divided by 2. It means this force will continue to these supports, and there is no reason, and I have got W times L over here as well, there is no reason that this force should not be transferred to left. In these options, I have option D, which is incorrect because we have a force over here that needs to be transferred. In this span, we have reactions here. It means that this option is not possible. Option A is not possible as well because here a pin is not transferring any shear forces over here. Only in that situation when we have reactions here as zero reactions. In that case, pin does not transfer shear forces, but here we don't have any zero reactions over here. We have some kind of force at this position. This means that this discontinuity of shear force is not possible. I can discard this option as well. And as I have this portion which behaves like a simply supported beam, looks like this, and its diagram is most of the time, if I draw anti-clockwise forces, this diagram is like this. This is equal. And only option here which has got this kind of diagram is option C. So option C should be correct option. Option B is the wrong option, but I will prove it with the help of some calculations to see what I'm saying is right or wrong. But in my view, option C is the correct one. This is the quick way to tackle these problems. Let me first of all draw this diagram. Here I have to take certain assumptions. I'm assuming that this loading is 10 kilonewton per meter, and I'm assuming that this load is W times L, and I'm assuming here that L is equal and it is 2 meters. This means that this load will be 10 times 2, which means it is 20 kilonewton. The first thing I would do is to draw its deflected shape, and that will really give me the direction of reactions. So this will deflect like this. This is the deflected shape of this beam. Call this point as A, B, and C. But here, for the sake of clarity, I'm assuming that all reactions are acting upwards, although reaction at A is going to act downwards. And we will see in calculations that if it is right or wrong. So VA, VB, and VC. The first step that I will take is I will separate this, and this part will have upward reaction, and again on the left side I will have a downward reaction. Because the distance is 2, so reaction here will be 10 times 2 divided by 2. So this will be 10 kilonewton on this side and 10 kilonewton on left side. Here it will be 10 as well. And then I will continue to draw this figure. I have a roller and I have a pin over here. This point is A, this is B, and I have load applied, that is 20 kilonewton. And here you have 2 meters, 2 meters, and 2 meters. I've divided it into two parts where we have this internal pin. And now I'm in a position to say summation of moment at A is equal to 0. I'm just taking into account the left portion, AB, and this overhang portion. So I will say plus 10 times 6. 10 is this reaction on the pin, and this is creating clockwise moment with respect to A. That's the reason it is positive. And I have this reaction which I've assumed VB vertical and VA vertical. So minus VB times 4 with respect to A, it is creating anti-clockwise moment. And then I have this load of 20 kilonewton. This is creating anti-clockwise moment as well. So 20 times 2 is equal to 0. If you simplify this, you will get VB as 60 minus 40. This is giving 20. So 20, if you take it on the other side, it will be negative 20. So negative will get cancelled. I will have 20 divided by 4, which means 5 kilonewton. If VB is 5, then I will say summation of all vertical forces equal to 0. Now here you have to note a very important thing. I have to say summation of vertical forces is equal to 0. And here summation of moment as well. Note that these things only apply to the left portion, not the entire beam. The entire beam is indeterminate structure, and we are dividing it into two segments where we have a pin. So when I divide it into a pin, it turns into two determinate structures. Summing up vertical forces, I have VA plus VB plus 20. 20 is this load minus 10, which is at the pin, is equal to 0. I've just determined VB. I will put value of VB. So VA plus 5 plus 20 minus 10 is equal to 0. This will give me value of VA as negative 15 kilonewton. And as I mentioned earlier, that reaction at A should be downwards. Once I've got all the reactions, then I'm in a position to draw the diagram. So let's draw the diagram over here. So now I have got all the reactions. Firstly, I have this 10 kilonewton. So I will start from right side all the time when anti-clockwise forces are positive. So here 10 kilonewton, and then it will drop down to 10, and it will continue, and it will go up by 5, and between here and here this is 5. Then it's 20 upwards. So 20 upwards means that I have 5 plus 15. So this will be 15. And between these 2 points, I've got nothing. And here, due to downward reaction, it will come down. So here it is positive and negative, negative and positive. This shows that the correct option is option C.